Welcome to egate.ai. So today we'll be solving an example problem for Bayes theorem. So this question is from the book by Sheldon Ross, and it is a very standard question which can be addressed using Bayes theorem. And let's take a look at how the question goes. So it says that a laboratory blood test is 99% effective in detecting a certain disease when it is in fact present. So the test is 99% effective when the person has the disease and you do the test on them. So the test will 99% accurately say that okay, this person has the disease. However, the test also yields a false positive result for 1% of the healthy persons tested. So if a healthy person gets the test done, then with a probability of 0.01, the test can say that test will imply that he or she has the disease. Now, the question asks like if 0.5% of the population actually has the disease, what is the probability a person has the disease given that his test result is positive? So a person gets to the laboratory, get the blood test done, and the result is positive. So what is the probability that the person actually has the disease, right? So let's see how we can use Bayes formula to get an answer to this question. So first, let us write down what are the two events occurring in this particular situation. So the first one is a particular person. A person has the disease, right? So a person is getting tested. They actually has the disease. Another event that is occurring is the test result is positive. Which can also happen when the person does not have the disease, right? So you see that with 0.01 probability, the test can imply that the person has the disease even when the person is actually healthy. Okay, so there are these two events. So let me write that down. Okay, so D is to say that the tested person has the disease, and E is if the test result is positive. Okay, so now let's also list down what are all the probabilities we already know from the statement of the question, right? So the first is this 99% effective in detecting a certain disease, right? The test is 99% effective when that particular person has the disease. So that's a conditional probability. So the test result is positive when the test person has the disease. So given the person tested has the disease, that probability is 99%, so 0.99, right? So the test is 99% effective in detecting that the test result is positive, like detecting the disease when the disease is itself present in the person tested. Okay, so that's P of E given D. Now what else we know? We know that 0.5% of the population has this particular disease, right? So irrespective of the test done or not, so even if you do not consider any test being done, we know that the population, like 0.5% of the population has the disease. So that's the probability of D. So the person has the disease, and that is 0.5%, so 0.005, right? So here, like if you want to consider, you can even not consider this one. So let's say D is the person has the disease even if it's not, like they are not tested. Okay, and from this you can already imply that the person not having the disease, that probability is 1 minus this, and that is 995, right? Okay, what else we know? Now there is another probability given in the statement, that's this 0.01. So with 0.01 probability, the test result says that the person has the disease even when the person actually does not have the disease, right? So that's P probability of E. So the test result is positive given that the person does not have the disease. So D not. So that it's given that that's 0.01. Okay, so these are all the probability and conditional probability values we already know from the question. Now what exactly the question is asking us to solve? So the question is asking you that, okay, so this percent of the population actually has the disease. Now a person goes to the laboratory, gets tested, and the result is positive. What is the probability that the person actually has the disease? So we want to calculate probability of D, so the person has the disease, given that the test result is positive. So probability of D given E, so the person has the disease given that the test result is positive, right? So now we have already covered Bayes theorem, at least a quick introduction to it, and we know that the formula goes something like this. So it's kind of a flipping of the conditional probability. So to calculate probability of D given E, we need probability of E given D. We multiply that with PD and we divide that by PE, right? Okay, now at this point, what do we already know from the questions? We know probability of E given D, that's already given, that's 0.99, and we also know probability of D, that's 0.005, but we do not know probability of E right now, right? We do not know that, so we need to calculate that. So how do we calculate probability of E? To do that, we can again use the conditional probability probabilities with the total probability formula, right? So using conditional probability, we can calculate the total probability. So that's probability of E given D multiplied by probability of D plus probability of E given D naught multiplied by probability of D naught, right? So we know the probability of E when the person has the disease, and we also know the probability of E when the person does not have the disease, and we can combine these two information to get the total probability for E. Okay, so let's put down the values here to get probability of E. So probability of ED, we already know that it's 0.99, and probability of PD, that's 0.005 plus probability of E given D naught, so when the person does not have the disease, so person is healthy, then the test result also comes as positive in 0.01 sorry, so in points with 0.01 probability, and the probability of the person not having the disease, we have already calculated that as 0.995, right? Okay, now putting all these values in here, so we get this probability of ED multiplied by PD, we already have that as well, so we have that, and then we also know P of E now. Okay, put that in your calculator and you'll get a value like this, right? So that tells you that if a random person goes to the laboratory, get the test done, and the test comes as positive, there is actually only 33% chance, 33% probability that this particular person actually has the disease even when the test result is positive. which may seem kind of surprising at first, right? Because it says that it's 99% effective in finding out that the disease is present in a person, right? But because such a low number of population actually has the disease, and the false negative rate in that sense is really high, that's why when you actually calculate the probability of a certain person having the disease when the test result is positive, that boils down to such a low probability like 33%, right? So hence only 33% of the persons whose test results are positive actually have the disease. Now let's look at a different interpretation, a second interpretation for the same problem, so that it becomes a bit more clear to you how this such a low 33% rate is coming, right? So let's take a different approach to solve the same problem. Okay, so in the second interpretation, let me first write down again like what are the things we know. Okay, so we know that in the population only 0.005 with 0.005 probability will have a person who actually has a disease. So that means that if we can test randomly 200%, then one of them will have the disease, right? On average. So one of them will have the disease. So let me write that down. Okay, the second information, we know that when the person in fact has the disease, then the test is 99% effective in finding out the positive result. That means that out of every 200% tested, so only one will have the disease, and the test will with 99% accuracy will tell you that a person has the disease. So the test is 0.99 effective in finding out that a person has the disease for every 200% tested, right? Because for every 200% tested, you actually have one person who is unhealthy, who has the disease. Okay, so the test will correctly confirm that 0.99% has the disease, because only one person actually has the disease. So the correct confirmation is 99% of that, only one person. Now the test result will also tell for few healthy person that the test result is positive, right? Because there is this false positive thing. So that's right. So probability of E given D naught is 0.01, and that means so out of every 200% tested, the test will incorrectly state that how many person has the disease. So healthy person 199, right? And then you have this probability 0.01%. So that means 1.99 cases, the test will say incorrectly say that this person has the disease. Right? So when 200% gets tested, only one of them has the disease on average, but the test will say 0.99% has the disease correctly, and the test will also say some other 1.99% has the disease who are actually healthy, who does not have this particular disease. So what is the effectiveness of the test now? So the proportion of time that the test result is actually correct when it says the result is positive, so the person is ill. What is the proportion that it's correct? So under this 0.99, when all the person for whom it has said that the test result is positive is 99 plus this 1.99 as well, and you calculate that, you get the same value as we are able to calculate using the Bayes theorem. So that's your 33% effectiveness of the test result. Okay, so that's your answer. And this is a very classic example. We will solve multiple such examples in the next videos, and also we'll solve actual previous year GATE questions. Okay, see you.